Today I'm going to talk about the project that I've been working on this past semester, which was using AI methods in medical imaging. So what is exactly the problem that we're working at? Well, to date, CT scans have been focused on answering the specific clinical questions. So if you were to go to a colonography, then the clinician will look at your colon section and see if there was any problems within the colon. But CT scans possess rich information about body composition that it goes unused in routine clinical practice. The cross-sectional nature of CT scans documents all structures within the prescribed range of imaging and leads to obtaining incidental information of other regions. Thus, there is abundant biomedical information that is not harnessed for further analysis. So why is this important? Well, 100 million body CT examinations are done a year, so there's great opportunity to obtain cardiometabolic information that is secondary to original clinical question. This is called opportunistic screening, and it uses this additional imaging data to obtain biomarkers for a wide variety of diseases, including osteoporosis, fatty liver disease, cardiovascular disease, and metabolic syndrome. Thus, it can obtain data in order to guide appropriate treatment, including more aggressive treatment for those at highest risk and protection from the costs and implications of unnecessary treatment for those with lower risk. So why do we need AI to solve this problem? Well, with AI, you don't need any additional time, medical personnel, and it is cost efficient. It automatically performs this assessment without additional resources, and it can be accurate, more accurate than current clinical measures. For example, the aortic calcification score, which is obtained from AI measures, is a better predictor of cardiovascular disease than the Framingham risk score, which is the conventional way of measuring risk for cardiovascular disease. In addition, the visceral to subcutaneous fat ratio obtained from AI measures is better at predicting future cardiovascular events and deaths than BMI. Just to provide a specific case study of the benefits of AI scores, you can see in this case study in the image below where a 52-year-old man conducted a CT scan, and the conventional measures showed that he had a Framingham risk score of 5% and a BMI of 27.5, which indicated that he had low risk for cardiovascular disease. But in reality, based on the AI measures, he was in the 97th percentile for cardiovascular risk, indicated by the Agatston score, and he was in the 99th percentile for the visceral to subcutaneous fat ratio, and in the 97th percentile for liver density, all indicators that he had high risk for cardiovascular disease. Thus, if AI measures were used instead of conventional measures, then it might have picked up on his risk for cardiovascular disease more accurately. So, how did our lab implement AI? Well, we used the MONAI framework, which is specifically used for creating healthcare image training workflows. We applied a 3D convolutional neural network to segment specific regions of interest, such as the bladder, kidney, aorta, lung, spine, etc. As you can see in the image on the right, what the algorithm does is it takes an input slice of a CT image, and then it segments the slice for specific regions, such as it segments the liver in the first image, and segmenting the kidney in the second image, and the aorta in the third image. Once the model does these segmentations, we then perform statistical analyses on the segmented regions to acquire biomarkers, such as the mean attenuation value, which can be an important assessment of indication for fatty liver disease. So to be a little bit more specific into our machine learning workflow, the initial step was to load in the data, and we used the CT-ORD data set which was a public data set of 140 CT scans, each with 5 organs labeled in 3D: the lung, bones, liver, kidneys, and bladder. We then pre-processed this data, applying normalization, cropping, resizing, and image augmentation, which was essentially applying random transformations to the data, such as random rotations, flipping, or random changes in the brightness of the image. And this data augmentation was performed in order to increase the diversity of the data sets and variation within the data set in order to improve the model's predictive capabilities. We then loaded the data into training loaders provided by the MONAI framework, and the training loaders would give out batches of data as shown below in the image, which shows a batch of data that indicates the original image and the label. The next step was creating the model. We used a UNetR model for segmentation, which is the state-of-the-art model and has shown to create really good segmentations. On the right in the image, you can see the architecture of the model. We also, for our loss function, we use the dice loss. And this is a common loss function used in image segmentation. And essentially, the way that dice loss works is it measures the overlap between the predicted labels and the original labels. For the optimizer, we used the Atom optimizer, and for the metric, we used a dice metric, which was similar to the dice loss, except the dice metric is used to as a measure of accuracy on how accurate the segmentation is compared to the real segmentation. Then we trained the model for 500 epochs, and in the image below you can see the graph of the average loss over the iterations it was trained over, and you can see that it decreased over time, which indicates that our model was improving. And on the right graph you can see that the dice metric was increasing, which indicates that the accuracy of the model was increasing as well. Just to provide an example of the types of segmentations the model was producing, on the right you can see the different images, input images and the output labels. In the middle is the original label, and on the right is the predicted label from the model, and you can see how close the predicted labels and real labels are. So like I said, the dice metric was on the order of 0.8 to 0.9, which was really good results. And the closer that a dice metric is to 1, it means that the original label is, the predicted label is more closer to the original label. So once we got those segmented regions, we performed statistical analyses on the predicted segmentations in order to obtain important biomarkers, including the mean attenuation value. So on the bar graph here, we did this for different subjects, and the bar graph is structured in a way that the mean is on the top of the bar graph, and the line here is the standard deviation of the predicted result. And so you can see here that if there was a CT-HU mean attenuation value of less than 40, then it might be suggestive of fatty liver disease. But in the bar graph here, none of the mean attenuation values were less than 40, indicating that the subjects that we performed analyses on, none of them were had risk for fatty liver disease. We also performed this on the spine, and if any of the HU values were less than 150, then it could be suggestive of osteoporosis. But in the analyses here, we saw that we conducted that there was no attenuation value of less than 150. And these are the sources that I've used for my presentation. And this concludes the overview of our project and what we have currently done. In the future, we hope to implement more different types of biometric indicators, and also we want to use this model on more data and increase the size and capabilities of our model. Thank you for listening and have a great day.